Welcome back to another explainer. So today we're diving into a topic that is literally foundational to the modern world around us. We are unpacking the fascinating civil engineering behind massive retaining structures. If you've ever driven on a highway, navigated an overpass, or hung out near a large-scale commercial development, you've been surrounded by these things. But the real magic making them possible, it's entirely hidden from plain sight. You've definitely seen these on your commute. A massive, finished concrete block wall running right alongside the roadway. We blow past them at 60 miles an hour without giving them a second thought, right? Because to the naked eye, it just looks like a neat stack of very heavy concrete blocks holding back a literal mountain of earth. But what you are actually looking at is a highly complex, heavily engineered composite structure. Which brings us to the big question for today's explainer. How exactly do millions of pounds of dirt stay perfectly upright? I mean, soil naturally wants to slope, slide, and spread out. Yet here we have sheer vertical drops remaining completely stable for decades. Well, we're going to demystify the hidden engineering that prevents these tower walls from just blowing out and falling over.
Here is our roadmap for today. First, we'll break down the anatomy of an RS wall. Second, facing systems and reinforcements. Third, we'll dive into understanding lateral earth pressure. And finally, we'll wrap up with internal and external stability.
All right, let's jump straight into Section 1, Anatomy of an RS Wall. Okay, so if we slice one of these walls open, here's a look at a typical cross-section. Notice how all the different pieces fit together like a giant puzzle. Down at the very bottom, you have a leveling pad resting firmly on the foundation soil. Moving up the front is the RS wall facing. That's the part we actually see from the road. But right behind that facing, you have layers of soil reinforcement extending deep horizontally into the reinforced fill. You've also got drainage media tucked in there to manage water, and finishing it off at the top is a coping beam and crush barrier. When we categorize these components, it's pretty brilliant how they interact. You've got the facing system and the soil reinforcements, tied together by a highly specific connection system. These elements work in perfect harmony with the reinforced fill, the engineered dirt, and the retained backfill behind it all. Throw in the drainage media to ensure water pressure doesn't randomly build up, and you've got a unified composite structure. The soil isn't just sitting there, it's actively engaged. Moving right along to Section 2, Facing Systems and Reinforcements. Now, the visual aesthetics of these walls can vary incredibly based on the project. Sometimes you get these discrete concrete panels. They offer that super clean, geometric, modern look you typically see on urban highway overpasses. But contrast that with gabions. Gabions are basically heavy-duty wire mesh boxes just packed with rugged rock. They give a much more natural, textured vibe and are incredibly durable, which makes them perfect for mountainous or rural highway projects. And the sheer variety in facing types doesn't stop there. You might see a geocell facing, using stacked, honeycomb-like cellular structures that give a highly distinct, almost woven texture to the wall. Or you might run into a concrete canvas slope, acting almost like a ready-made mattress of concrete that creates a smooth, continuous, striped surface. But here's the real kicker. No matter what the outside looks like, it's what is firmly attached to the back of these facings that matters most. And that brings us to the reinforcements themselves. Take geostrips, for example. These are specialized uniaxial materials used to hold everything together. They're made of high tenacity, high modulus polyester tendons safely encased inside a polyethylene sheathing. These strips are the absolutely crucial tensile elements buried layer by layer in the dirt. They bond with the soil through simple friction to create a stable, reinforced grid structure that totally transforms the structural capacity of the loose dirt. Which leads us to the invisible physics making this possible. Section 3, Understanding Lateral Earth Pressure. The foundational geotechnical concept we really need to grasp here is lateral earth pressure. Simply put, this is the pressure that soil exerts in the horizontal direction. Think about it. If you dump a load of sand, it doesn't stay in a perfect straight column, right? It spreads outward. Soil naturally wants to slide and expand laterally. In geotechnical engineering, we categorize this pressure based on how the retaining structure moves relative to the actual mass of the soil. We have to draw a really sharp distinction between the two main types of dynamic lateral earth pressure, active and passive. Active earth pressure occurs when the wall undergoes tiny deformations and actually moves away from the backfill. The soil is basically trying to escape and expand horizontally, and its internal shear strength steps up to resist this movement. On the flip side, we have passive earth pressure. This happens when the wall is pushed into the backfill. The soil is being compressed here, and its shear strength is fully mobilized to resist that compression. Think of active pressure as the dirt trying to shove the wall over, and passive pressure as the dirt stubbornly refusing to be squished. All right, final piece of the puzzle. Section 4, internal and external stability. This concept brilliantly illustrates the high-stakes underground tug-of-war happening constantly. Imagine a diagonal plane cutting through the soil. We call it the failure plane. On one side of that plane is the active zone. The soil here is in a state of active earth pressure. It is desperately trying to slide outward and push the wall facing away. But remember those soil reinforcements? They stretch right through that failure plane, deep into the stable resistant zone, also known as the anchorage zone. As the active zone tries to pull out, the load is immediately transferred to those reinforcements safely anchored deep in the resistant soil. To really appreciate the math here, we can look at what geotechnical engineers call Rankine's theory. Let's say we have a typical soil with an internal friction angle of 30 degrees. The coefficient of active pressure, or Ka, calculates out to about 0.333. Meanwhile, the coefficient of passive pressure, Kp, calculates out to exactly 3.000. Now, passive pressure usually acts at the toe of the wall, which is the part embedded below ground at the very front. As the active pressure from the massive pile of dirt tries to push the wall forward, the embedded toe pushes directly into the soil in front of it, generating massive passive resistance. So, the absolutely crucial point is this number right here, 9. If you compare that passive coefficient of 3.000 to the active coefficient of 0.333, you realize that the passive resistance at the embedded toe is exactly 9 times greater than the active pressure pushing against it. 9 times. That is exactly why embedding the bottom of the wall into the ground is such a powerful, game-changing stabilization technique. Because of all this incredible internal friction and anchorage, engineers from the outside actually treat this entire reinforced dirt block as a single, rigid gravity structure. For external stability, they have to check 3 critical things. First, sliding. The whole massive block cannot slide forward, which is stopped by friction at the base and that crazy powerful passive pressure at the toe we just talked about. Second, overturning. The wall absolutely can't tip over, which is resisted by the sheer immense weight of the reinforced block itself. And third, bearing capacity, ensuring the foundation soil beneath the structure is tough enough to support those massive vertical loads without sinking. It totally shifts your perspective, doesn't it? What looks like a simple pile of concrete panels is actually a finely tuned system of geostrips, shear strength, and friction zones perfectly balancing active and passive earth pressures. So next time you're driving past a highway wall, will you just see concrete, or will you see the invisible tug of war holding it all perfectly together? Thanks for hanging out with us on this explainer, and stay curious.